Hey everybody, this is Mr. Gunnell again. Today we're going to look at lesson 3, and we're still looking at some of the graphs of simple harmonic motion, but we're going to focus a little bit more on the equations this time. So if you notice in the lesson, we start out with the do now of defining SHM, or simple harmonic motion. This is really important for one of your objectives for the IB is knowing how to define simple harmonic motion. And again, that's all really simplified by that equation that we had mentioned before, where we say that the acceleration is proportional to displacement, but in the opposite direction. And you're expected to know what that negative sign means. So anytime you're asked to define simple harmonic motion, you should say that the acceleration is proportional to and in the opposite direction of the displacement. And again, we do want to make sure that we're talking about the displacement from equilibrium. Now, one of the things that we didn't mention last time is that there are a few requirements if you're going to follow SHM or for any object that's doing so. One is that the period and your amplitude have to stay constant. If those are not staying constant, something else is going on. Remember, the period's constant, we call that a periodic oscillator. If the amplitude's changing, a lot of times what that means is there's some driving force, somebody's pushing the oscillator, or maybe there's some friction, so it's slowing down over time. It's also important to know that the period is independent of amplitude, so for a spring oscillator, for example, if you pull it back further, it's still going to have the same period, or for a pendulum, same thing. It just happens to be that if you pull it a little bit further or displace it more from equilibrium, it's just moving faster, so that balances out. And so those don't depend on each other if it's simple harmonic. We also know that the graphs of position, velocity, and acceleration are sines and cosines. That's what we looked at in lesson 2. And also one really important thing is that the equilibrium position has to be fixed. So for a pendulum, for example, we want to make sure that the top location is not moving anywhere. We don't want that equilibrium location to be moving around. If it does, then it's no longer simple harmonic. Now, one thing that's important to understand before we get into some new content is defining what's called angular frequency. Sometimes when we're looking at circular motion, we'll call this angular velocity or angular speed. But all this really refers to is the angle you move through in some amount of time. Now, the symbol we use for this is a Greek letter. It's an omega. It looks kind of like a curvy W. And there are a few different ways we can look at this in terms of an equation. Now, if you look at the definition, we say it's the angular displacement per unit time. And that's really what its equation is. So we say that the angular frequency is the angle that we go through. So I'm going to call that delta theta and divide that by the time that it takes to do that. So a lot of times if this is something that is circular, we talk about the angle that it rotates through. If we measure from a radius, that's not a very good circle. But some angle theta that we move through, and then the amount of time it takes to do that. So that's how we define angular frequency. And again, I'm going to get rid of that because it's not really a very good circle. But we should understand what that means when we say angular frequency. Now, a lot of times we'll simplify this. We'll say, for example, if something goes through a full cycle or a full rotation, we call the time it takes to do that the period, and if you remember from last lesson, we called that capital T for period. It's just a specific time for one full cycle. And also, if we're talking about one full cycle, if we go through some angle in a full cycle, that's one full rotation, or we would say, in terms of the angle, it's 2 pi. And by the way, when we're doing this, we're always measuring theta in radians. It doesn't really work for us to use degrees in this topic. Now, one other way that you could write the angular frequency, since we know also if we kind of focus on this part, like divided by time or divided by period, that's the same thing as saying frequency, because frequency and period are inverses. So another way to write this is 2 pi times f. And so those are several different options. A lot of times we focus on those last two, just because we're typically dealing with one full cycle. But we should definitely understand where that comes from, which is that it's the angle we move through in some amount of time. We're just being more specific with those other two formulas where we do one full cycle, or if we happen to know what the frequency is, we can use that. Now, again, the units for this, since we measured the angle in radians, we're going to say that the units are radians and then divide by time, so we say radians per second. Or another way we could write that is just radians seconds to the -1. And there's not really a direction on this, it's just what angle we're going through. And we don't really measure like clockwise or counterclockwise, so we're just going to say that this is a scalar measurement. Okay, so again, we need to make sure we understand what angular frequency is before we move on to this next part. And I'm going to be using that a little bit in these equations. So if we look at this next example, because it's easier to talk about the equations given some example, we're going to imagine that there's this mass that's going up and down on a spring. Again, like we looked at last time, it doesn't really matter if it's going up and down or horizontally. We're still going to graph if it's a spring hanging from the ceiling, for example, and it's just oscillating up and down. At some point in the middle, there's an equilibrium location, and it goes up and down between those maximums where we say it's XO or A, sometimes we'll use for amplitude, and then negative XO for its other amplitude. And again, those are not measured from one end to the other, they're always measured from the middle, from the equilibrium position. So in the question, they say that it's released from rest above its equilibrium position. So they're starting it out at the top position here. It's going to go down and kind of just oscillate up and down between those 2 points, and we're going to graph what that motion looks like. And so if it's starting from the maximum position, our graph, instead of starting from the middle like it did last time, is going to start up here at XO. And then I've written this out to show those quarter, half, 3/4, and a full period. So if we map this out, I'm not going to go through it the same way I did last time, but it's going to start at the middle. It's going to go through equilibrium at a quarter period. It's going to end up on the other side halfway through, come back, and then be there. And then this is going to look this time like a cosine wave, or a cosine graph, I should say. And so we can also label those other spots. The top was XO, and here's negative XO because that's the other amplitude. We always assume, as we mentioned up here, that for something that's simple harmonic, the amplitude is constant. And that shows up in our graph in that we don't get the amplitude getting smaller over time. It keeps reaching that same location. So if we think about the graph, we notice that that's a cosine wave or a cosine graph. But what we really want to do is we want to write that out sometimes as an equation. And so if I write this out in the way that the IB would like us to, I'm going to move this over to the side a little bit more, is the way we'd write that is if we wanted to figure out the location of this at any time, we can say that some location X, wherever it happens to be in its oscillation, is going to be based on the fact that we know it's a cosine graph. And so it's going to be cosine of something. And whenever we make an equation with a cosine, we want to talk about the amplitude that it gets to, because that's going to multiply the maximum value of cosine 1 with the highest it could be. So that's going to end up being x naught, or our amplitude out front, to scale up what that cosine is going to give us. Now, inside of that cosine, we're going to have an omega times t, because we want to look at basically the angle that it's going through at any point. What this will do in terms of giving us an angle is because we go through some delta theta over time. When I multiply that by the t that's in there, those will cross out the t's, and then it'll give us the angle that we've gone through. So we really are taking the cosine of some angle. So that's why we're using the omega in there. Again, I'm going to remove this because we can calculate omega any of those different ways. We can do 2 pi over t, we can do 2 pi times f, but we should know that as this is written, there's usually going to be some omega in there to represent our angular frequency. So I'm going to label some of these. This is the position that we'd have at any time. XO, again, is our amplitude. Omega, we already mentioned, is our angular frequency. And then T is just the time that's passed since the oscillations have begun. And again, we do have several different equations for angular frequency. You could put units on these if you wanted to. Positions in meters, amplitudes measured in meters. Angular frequency is radians per second, and then time just in seconds. Now, one thing to really mention here is that since this is in radians, when we're doing calculations, if we're going to take the cosine of this, we need to make sure that our calculator is in radians. That's really important, especially in this topic, is that our calculator needs to be in radians mode. And it's because of how these angles are being used in this topic. Okay, so that's looking at our position. Now, if we use that to think about velocity, just like we did before, we can look at the gradient of that graph to get our slope for the velocity graph. We could also look at a derivative. It depends on how you want to look at this. But I'm going to just jump right ahead, and so say at the beginning we're going to have zero velocity. Again, that also is because it started from rest. It's moving with a negative velocity down here, zero again, positive velocity, and then back to zero. And I'm only going to do one full period this time instead of two. Now, if you remember last time, I labeled this as Vmax and negative Vmax, which you can do, but this time I'm going to label it a little bit differently. So if I take from this equation that we started with up for the position, and I write one for velocity, this time our velocity is going to be related to a sine graph because it's starting from the origin, and so I'm going to say sine of something with the same angular velocity in the same time. Now, this time again, because we're starting out, or our maximum position is Vmax, we can write Vmax out front because that's going to scale the size of our sine graph. Just as before, the maximum minimum sine can be is 1. So if I really want to get those extremes, I have to multiply by what the amplitude is. The amplitude of the velocity. Now, the way that this graph is written is that this is a negative sine graph, so I'm going to put a negative out front of that. And so this is the equation that would describe this specific graph. It's not for every velocity, and so that's why we want to think about what those graphs are going to look like each time that we do this. So that's using the velocity in our equation. But one other way that we can write this is we can use the amplitude and the angular frequency to really talk about what that velocity is going to be. So we can also write this as V equals negative omega times x naught times the sine of omega t. Now this is the equation that the IB would like you to use, is knowing this one, and I'll highlight this one up here because this is also important. Those of you in calculus might see this as being just the derivative, is that we take the derivative of the position equation, and then the derivative of the cosine graph is going to be a negative sine graph. And also, since we're taking the time derivative, if we use what's inside of the cosine, that omega t, that's going to bring an omega out front and leave us with negative omega x naught sine of omega t. If you're not in calculus, you're not expected to know that, but that is pretty important to know what that equation is when you're done. So instead of labeling these as V or instead of Vmax and negative Vmax, I'm going to take those and write them as the equations that we should have, or in relation to the amplitude. So this is omega times x naught, and this is negative omega times x naught. We could, again, also label those as Vmax and negative Vmax. Okay, but important to realize that we can write them with just the amplitude. Now, if you look in your data booklet on page 9, you're going to see those same equations with x and v, and you're going to see that written as omega x naught sine of omega t. Now, they actually give you both options for a different couple of types, but I can show you guys that a little bit later. Now, the final graph that we get to is going to be your acceleration. And when we draw out the acceleration, we're going to use our velocity graph, and we can look at the gradient again. Or also remember it's going to be flipped from your position graph, because acceleration is proportional to your displacement, but in the opposite direction. So if the position graph is a positive cosine, the acceleration graph is going to be a negative cosine. And so when I do this graph, we're going to say that it's going to be, I already lost it. There we go. And that's through one full period, and we're measuring time on that axis. And just like we've done before, we can say that acceleration is a max, or the maximum acceleration we get, times this time it's again a cosine graph of omega t, but it's a negative, so I'm going to put that negative out front. And the same thing as I mentioned before, if you're in calculus, you'll know that this is just a derivative of the velocity graph. So one way we could write this is the acceleration at any point is equal to now negative omega squared x naught times the cosine of omega t. And so this is the one that I'd like you to think about when you're using your equations, is that it's true that this first equation I've written does work, and it talks about our acceleration based on our maximum, but it's really important to always refer to that in terms of the amplitude and your angular frequency. And so those are always really important to think about. So I'll leave those highlighted because those are really the three important graphs that we're dealing with. Again, this is for the velocity at any point, and this is for the acceleration at any point. So as I had mentioned, like those of you that are in calc, you're going to know that these just follow derivatives as we're going through the graphs. So it's going to be pretty helpful to always think about it in that terms, or in those terms. And so, for example, if we're following the patterns of derivatives, if we have a positive sign, take the derivative of that, and we go to a positive cosine graph. Take the derivative of that, we go to a negative sine graph. Derivative of that is negative cosine, and it can just keep going, and it's going to cycle through to positive sine, and then positive cosine, and it's just going to keep going. And so wherever we place our first graph for position, we can just follow that pattern through. So if we look up here, our first graph was a positive cosine graph. So we start here with position. That means our next graph is going to be velocity, because we're taking the derivative. It's going to be a negative sign, which it was for us up here. And then we're going to keep going, and then we're going to have the acceleration. So it just kind of is always going to keep following that pattern. And let's say we had started with a negative cosine graph for our position, then the velocity would have been a positive sine, and the acceleration would have been a positive cosine. So always be thinking about that. You can use calculus connections if you are taking calculus, and if not, then these formulas are provided to you in some variation on the reference table. And again, this is subtopic 9.1. It's on page 9 in your reference table. Now, the other thing to think about there, and actually before I get to this, is there is one other equation on your reference table where if you look on page 9, we know that the acceleration is equal to negative omega squared times x. And that should make sense because we actually have an equation that we just came up with up here. I'm going to zoom out so you can see both of these, is that we have this equation for x. And if we plug that whole thing in, we would get negative omega squared times the whole x equation, which is x naught cosine of omega t. And that is just this equation. So while the IB is not going to give you this specific equation, they give you the other two. They're just expecting you to take whatever your x equation is and just multiply it by negative omega squared. And hopefully that should make sense, because this follows our rule for simple harmonic motion. When we define simple harmonic motion, we said the acceleration is proportional to displacement and in the opposite direction. And that's the equation that shows us that without just saying proportional to. So you should definitely be thinking about this equation that's also in your reference table. That's another really important one, and how it gets us to this last equation. Okay, so that was a lot of information about what those equations are and how we use them in a graph. I thought the next thing that would be important is to go through an example, and we can look at this one with an oscillating oscillator, which is a little repetitive. It's got a frequency of 5 hertz and an amplitude of 0.3 meters. Now, one thing that I should clarify is it says it's got a frequency of 5 hertz. There's two things that this should tell us: that this is just regular frequency and not angular. They'll be pretty clear in a question if this is angular frequency, and if it's not, we just assume that it's regular frequency. The other thing that tells us this is a regular frequency is this hertz unit. Frequency is measured in hertz, whereas the other is measured in radians per second. And they also give us the amplitude here of 0.3 meters, and that tells us that that's equal to x naught. So if we're going to write out these equations, we can actually take our rules from up above. Now, the thing that we need to think about here is we can't just always assume that this is going to be a cosine graph for the first one. So we don't just jump right to that. We need to use information in our question to help us figure out what that first graph is going to be. So if it's beginning at equilibrium, that's going to mean somehow it's going to have to be a sine graph. And the reason that we know that is if it's starting at the origin, that's going to be a sine graph. Now it starts moving in the positive direction, and some people actually, if this is confusing, might think about drawing the graph first. And so if we look down here at this position graph, if we know that we're starting at the origin and we're moving in the positive direction first, that means that our graph is definitely going to be a sine graph. We can also graph out the entire thing. Even though this is the next part of the question, I think it might be helpful. And again, we're taking that information from the question, starting at the origin and moving in the positive direction first. So when we write our position equation, we're going to say that the location, or the x, is always going to be based on, again, we start with the amplitude, and then the sine of omega t. Before in the notes, what we had done was use cosine, but it's a sine graph. And this is also written on page 9 of your data booklet. If you look, the first equation for position is x naught sine of omega t. They do also give you the other option if it's a cosine. So those are kind of not interchangeable, but you choose the sine or cosine depending on what your object is doing in the first moment. So now that we have that, that's a generic equation. We want to actually use some numbers if we have them. And so our position is going to be dependent on its amplitude. So we know that this is 0.3 meters for the x naught. And then sine, we're not going to do anything with this just because we're trying to write out the equation. It's sine, but now we want omega. But since we don't actually know what the angular frequency is, we just know what the regular frequency is. There's a couple of different options here. We can do the delta theta over t, and then I'll go back up and show those. We can do 2 pi over t, or we can do 2 pi f. Now I'm going to pick this 2 pi f equation because they've given us the frequency in the question. So that should actually be pretty easy to just go ahead and plug it in. 2 pi times 5 hertz. And then we just leave the t because this is just a generic equation that, well, not a generic, it's specific to our example, but we want to have an equation that could help us solve for any amount of time. Now I'm going to simplify this. I'm going to take out my units, but I'm just going to say this is 0.3 times the sine of 10 pi t. And so in the question, if we wanted to know where this object was at some time t, we could just plug in what the t was. Now, if we look at the velocity equation, again, we can use the same rules from up above. Our first graph was a positive sine graph, so that means that our velocity graph is going to be the next one. It's going to be positive cosine. And if you don't remember that rule, again, these are also on page 9 of your data booklet. The third and fourth equations are what, if the position is a sine graph, it says that the velocity is a cosine graph. And so we're going to say our velocity is going to be equal to omega x naught times the cosine of omega t. And then we can plug in those same values that we had before. We know that omega, we just calculated this up above in the first part of the problem, is 10 pi times our amplitude of 0.3. And then it's cosine of, really it's just what we had above. We had the omega times t, so I'm just going to simplify that right away to 10 pi times t. And so that should be pretty easy to simplify. 10 pi times 0.3 would just be 3 pi cosine of 10 pi t. Oops. And then again, with the last question that we're looking at, all that we really have to do is just take a negative omega squared times the x equation. So our acceleration is going to be negative omega squared times exactly what we had up in the position equation. Negative omega squared times x naught, sine of omega t. And so we're going to do this time negative, and then our omega is 10 pi. We're going to make sure we square that, and times 0.3. Sine of, and again, 10 pi times t. And that's going to simplify to, I believe we're going to have negative 30 pi. Well, negative 30 pi squared, sine of 10 pi t. And so those are really the three equations that we're looking for. We have a position, we have a velocity, and then we have our acceleration. And as I mentioned before, if you're a calculus student, you might just, instead of doing the equations over and over, you might take the derivative of the position graph and then the second derivative to get the acceleration graph. Okay, so as long as you have some method that will work for you, then you should be okay. Now let's go back down and finish up those graphs that we were talking about before. Our position graph is a positive sine. We can also use these equations if we feel like it'll be helpful to us. Our velocity graph is going to be a positive cosine graph. I'm going to freehand this. I could be also marking those points, but I'll just go a little quickly. Again, this is as time goes on. And then our acceleration graph is going to be the flipped version of the position graph. So if that's a positive sign, this is going to be a negative sign, which is also in our equation up above. Now, since we do have what those maximum and minimum values are, we should be labeling those on our graph. So I'm going to look up here at these equations we have, where we have 0.3, 3 pi, and negative 30 pi squared. Those are the maximum values for each of our graphs, so we want to make sure we put those on the axes. So their position, I'm trying to get this all on the same page, this maximum and minimum are going to be 0.3 and negative 0.3. We should also put units on those because that's position is meters. Our maximum velocity up here is going to be 3 pi, and then this is going to be negative 3 pi. And if we're putting units, that would be meters per second. We could also label this on the axis label also instead of putting it on the individual values. And then the acceleration, same thing. We have a maximum, a minimum. This time we have that negative is there just because it's one of the two. So this is going to be the negative 30 pi squared, and this is going to be just the positive 30 pi squared. And that's meters per second squared. And again, we could have put those units up top as ms negative 2. It's really kind of, I guess it's more correct to put them on the axis label, but either way is fine for right now. So that's how we get our graphs. You don't always have to label those maximum values, but might as well since we have them. And again, that was really through one full period of motion. And then the last part of this question that we want to look at is we want to look at what the displacement was at 0.17 seconds. Now this is the whole point of using the equations up above, is that now that we have equations for where it is, how fast it's going, and what the acceleration is at any one time, we're going to use that equation that we came up with, this 0.3 sine of 10 pi t, as our position equation. And since we have the time, we just plug that right into t. And so our position is going to be 0.3 sine of 10 pi times 0.17 seconds. And that will give us a position in the end, if we calculate that through, of negative 0.24 meters. So that should walk you through an example of one of these questions of what we would see in terms of using those equations, how that can relate to the graphs. And I hope that what we did up above helps you understand how we're getting those equations. And if you are in calc, definitely use that connection to help you understand these a little bit better. Okay, thank you.